Okay, we're going to do an example of a 3 by 3 Markov matrix. We're going to work with this example. Um, so the numbers on each column have to add up to 1 because they represent probabilities. So 2, 3, and 5 is 10 tenths, because those are tenths of a unit. So that is 1. 7, 10, and then 8 and 2 is 10. So here we have a good probability Markov matrix. And one application is this. Pretend we have 3 places, P, Q, and R, and we got individuals, whether they're birds, humans, animals of other kinds, that move between the places. They can be cities or regions, whatever you want to call. And then there is an individual who's in this place can every year may have a choice of staying in that place or moving to another place or to this place, and they can move in different directions. And let's pretend this happens once a year. Perhaps in the winter they cannot move, but once the summer, or the other way around, whichever season they choose to move. Or if we are talking about humans, it could happen over over the whole year. 2% stay in the same place, 3% move. Let's say we are in Michigan and they're going from West Michigan to East Michigan, and then they go, to, I don't know, Indiana, perhaps. I don't know. It is just a pattern that occurs that, people or animals may stay or move to one place or move to the other place, and because they have to add up to 100%. So think of this as percentage. That is kind of helpful. This is 20%, 30%, and 50%, which is a lot. Typically the numbers are not that large, I think, but it's easier to work out this problem on paper if we have those fairly big, large numbers. So 2% or 20% rather move. They don't move, rather. 30% move to place Q. 50% move to, which is a lot, place R. But then the population here also moves around. Some of them stay, 20%, 50% move back. Now that doesn't necessarily mean that the people or the individuals who came here are the same individuals that came here are the same individuals that go back. It could be that some of the ones in which the previous period did not move now are moving. So these are probabilities. They're not single individuals, but they are probabilities, which means it has to do with large populations. And the same thing here. Somebody may say, wait a minute, so this means that the population stays stable. Well, the population number, yes, because stays stable because perhaps 30% go here, and then, well, I shouldn't say that, because what if the populations are different sizes to start with? So 30% of this may not be the same as 30% of that. Anyway, so this is, yeah, the problem can get much more complicated, and this is only with three places. Of course, we could have way many more, or we could have fewer, I suppose, just two places, which means we have a 2 by 2 matrix, which is simpler. This is a larger matrix, a larger problem. And we want to answer some questions. So assuming we start in P, what is the probability that we stay in P after one interaction? Now, this happens once per period. This movement happens once per period, whether that period is 1 year, let's just say it's 1 year, or 1 semester, or 1 month. It depends. There's a cycle where things are moving, and then perhaps things are not moving for a moment, and we stop there and we start a new cycle again, and things are moving. And it could be as simple as just every December 1st we start a new cycle, or December January 1st rather. So after one cycle, what is the probability that if we start in P, we stay in P? And of course, the probability is 20%. 0.2 is the same thing as 20%. So the probability that we start in P and we end in P after one cycle is 20%. Okay, now we want to ask the question, what about the probability that we go back to P, the probability that if we start in P, we stay in P after, say, 10 cycles. Okay, so now the next question, or the first question we want to ask. There's two more questions we want to ask. So the first question is probability that if we start in P, we end in P after one cycle. And of course, what is the probability? And it is 0.2, so that is the answer, which is the same thing as 20%. And that's just straightforwardly from the diagram and from the matrix. By the way, we're assuming that this column represents P, Q, R incoming and P, Q, R outgoing. So if somebody comes from P, what is the probability it stays in P? 0.2. If somebody comes from Q, what is the probability that that individual goes to P? 0.3. So Q, 0.3. And then the probability that if somebody comes from R and goes to P is 0.5. Yep. Okay. So that is easy to answer. Second problem, we want to know the probability that if we start in P, we end in P after, let's just say 10 cycles. Oops, cycles. And I don't know the answer yet. Well, that's one of the things we want to find out. So what is that probability? If we start in P, what is the probability that we end up in P after in cycles? And 3, what is the probability that if we start in P, we end up in P after infinitely many cycles? So if we keep doing this process over a long period of time, 1,000 years or so, if an individual started here, what is the probability that that individual, well, that's kind of silly because an individual is unlikely to live 1,000 years, but let's pretend we could. What is the probability that that individual will stay in that place? Yeah, infinitely many cycles. So again, we don't know the answer. We're going to leave it blank for right now. And that's part of what we are going to do. So an individual starting in P can be thought of as, so an individual starting in P can be thought of as the vector 1, 0, 0. So that means pretend you are just thinking of one individual or 100% of a population starting at P and see where that population goes. But you can ask the same question as if, let's say 50 or one individual starts here and one individual starts in Q, where do they end up after a number of cycles of this migration that is occurring? Let me re-answer this question using matrices, because that can help us understand how we're going to answer the second question. So the way to answer the first question, an algebraic way to answer the question, is to multiply the original matrix 0.2, 0.3, 0.5, 0.3, 0.4, 0.3, 0.5, 0.3, 0.2 with 100, and of course that is going to give us a 0.2, which is the answer that we're after. 0.3 and 0.5. Yeah, so actually that is telling us the so if an individual starts at P, location P, the probability that that individual ends in population in location P is 20%, in location Q is 30%, and in location R is 50%. So this vector tells us not only the probability that an individual starting in location P ends in location P, but this vector tells us the probability that an individual starting in location P, and this one means P. If the one was here, it would mean Q, and if the one was there, it would mean R. But this vector tells us the probability that if we start with P rather, we end up with in P or in Q or in R. Okay, so if we want to answer the second question, we want to do this process 10 times. So we want to take this matrix and multiply this vector, which indicates that we're starting with an individual in location P, and we're going to multiply with A, 0.2, 0.3, 0.5, 0.3, 0.4, 0.3, 0.5, 0.3, 0.2. 10 times. Now, we're assuming we don't have a graphing calculator. Yeah, because we want to understand a process that is way simpler. Even if we had a calculator, if we do things, or a computer program, if we do things in a way that is not very efficient, and this is not very efficient, even with good technology, it could take a long time. We can end up with a loop that eventually just doesn't get out of it. So it's probably a good idea to think this using eigenvalues, eigenvectors, and trying to write this as another matrix in which we end up with a diagonal matrix, because then taking the power of a diagonal matrix with 10 in it would be way, way simpler and easier to do. Yeah. So the first thing we want to do is find the eigenvalues of this matrix, then the eigenvectors, and then we're going to multiply by a matrix X of eigenvalues. We're going to diagonalize this matrix, but let me show you the process. The diagonal matrix, let's label it as D. So our next goal is to write A as, say, XD, where D is diagonal, X inverse. Why? Because if we achieve this, then we will have that A to the 10 will be x d x inverse, so that's 1, x d x inverse, that's 2, x d x inverse, that's 3. Well, we're going to do that 6 more times, so that's going to be 9, and then we're going to end up with x d x inverse, all right, where d is diagonal. But then, so those are 10 of those. Multiplication by a matrix of matrices is associative, so we can regroup in any way we want. Initially, we start with those 3, multiplying with this 3, multiplying with those 3, and so forth. But then we can reassociate, so those 2 could be multiplied by those, but those 2 are inverses of each other. So we end up with the identity, just like a 1. The identity matrix, and multiplying the identity matrix does not change anything. We can cancel out those 2. That's essentially what happens. Those 2 cancel off, and this one will cancel with the next one, and that x cancels with the previous one. In other words, eventually those 2 cancel off, and we end up with x. All the x's in between and x inverses cancel off, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 x inverse, because all the x's in between cancel off, or x d to the 10 x inverse. And this is way simpler because d to the 10 is going to be way easier, since d is going to be a diagonal matrix, and multiplying a diagonal matrix is super duper duper super duper easy. Okay, so let's try to find the eigenvalues of this matrix. Now there's, I'll tell you the trick. There's a trick to this that we're going to use. Let's say you have, well, let's start by writing down the 0.2 minus the lambda, 0.3, 0.5, 0.3, 0.4 minus lambda, 0.3, 0.5, 0.3, 0.2 minus lambda. And remember, the way we start out is by finding the determinant of this matrix. So we're going to do the determinant of this to obtain the characteristic polynomial. And that's going to be, initially, it gets to be fairly long. So 0.2 minus lambda. And then we're going to multiply with those. So 0.4 minus lambda, 0.2 minus lambda, and then minus 0.09. So I'm going by this row and expanding the determinant. So minus 0.3, and then multiply those 2. So we have 0.3 times 0.2 minus lambda, and then minus 0.15, and then plus 0.5, 0.5 times 0.09 minus 0.5 times 0.4 minus lambda. So what I'm going to do is pause the video and get ahead myself, so that you don't have to watch all the computations that are going on. But I'll probably show them on the screen briefly so you can see them. Okay. I did some computations. Took me a moment. So I think I left it here. And then the next step was to multiply this out. So here it is, the multiplication, keep that there. Distribute this. So I distributed that and distributed that too. So it's a good idea to do this step by step. And then simplify those brackets. So this is just basic algebra. And then distribute. The next step is to distribute those two into the simplified brackets, and then this negative 0.3 into that, and then that 0.5 into that. And I did that in 4 lines, so I can add the terms more easily. You know, so I multiply the negative lambda times that, and that gave me the first line. And then the 0.2 times that, and that gave me the second line. And then the 0.3 times that, that is the third line. And the 0.5 times that, and that gave me this. And I lined them up so the cubes, squares, lambdas, no lambdas are on the same columns. But this is just, this is not a matrix or anything. This is just my way of writing the terms so I can add them together nicely. And here we got the what is called the characteristic polynomial of the original matrix. And we want this characteristic polynomial to be equal to 0. So, so we want this to be 0. This is a want. There we go. It's not like it is always equal to 0. It varies depending on the value of lambda, but we wanted it to be 0. So I like to work with my polynomials. I prefer my polynomials to be to have a positive 1 or a negative 1 as a leading coefficient. So I'm going to multiply the whole thing by negative 1 just to have a nice positive here. So multiply by negative 1. And we end up with lambda cubed minus 0.8 lambda squared minus 0.23 lambda. I had made a mistake there when I was adding this. When I was pausing the video to do the computations, I realized I had made a mistake. So I fixed it. Minus 0.0, oh, wait a minute. So I'm changing signs. So plus, minus, minus, plus, plus, minus, minus, plus 0.3 equal to 0. And here's the trick. When you are doing a Markov, when you're working on a Markov matrix, the number 1 is always a solution to the characteristic polynomial, always. So, I mean, because factoring this or trying to find the solutions may be rather complicated, but if we know one solution, then we can factor this out. We can apply synthetic division, and I'm not going to reteach synthetic division, but let me just show you how we do it. So 1, negative 0.8, negative 0.23, and positive 0.03 are the coefficients of the polynomial. And if we are dividing by 1, rather not by 1, by lambda minus 1, so we use synthetic division to divide by lambda minus 1, because again, 1 is always a solution of the polynomial. And in basic algebra 2, maybe college algebra, you have seen that if you divide by lambda minus 1, you get the other polynomial. Anyway, or rather, if 1 is a solution, then lambda minus 1 is a factor of the polynomial. So that's why we divide by lambda minus 1. But you can use long division if you wanted to, or we can just use synthetic division. So 1 times 1 is 1, but then we add those two, so we end up with 0.2 times 1 is 0.2, so 0.2, and I'm going to put a 0, and that is going to give us negative 0.03 multiplied by 1, and we get negative 0.03, and that gives us 0, which is what we want. That means that indeed 1 is a 0 of this polynomial, but that this synthetic division gives us more information. It tells us that the polynomial that is the second polynomial that this factors into is lambda squared plus 0.2 lambda minus 0.03. So this is what I'm trying to say. This equation may be written as lambda minus 1 times lambda squared plus 0.2 lambda minus 0.03 equal to 0. It's just algebra 1 or algebra 2 the most, for sure pre-calculus, that we can use synthetic division to divide this polynomial and get those two polynomials. But now this one is a quadratic, so it is much, much easier to solve. I'm going to solve this equation. I'm going to try to figure out the zeros for this polynomial by using the quadratic formula, because factoring, I don't know how to. I mean, I can try to, but might just as well start figuring this out. So remember, this is A, B, C. So the opposite is negative 0.2 plus or minus the square root of this guy squared, which is 0.04 minus 4 times, but then there's another minus here, so that is really plus 4 times A, which is 1, C, so that is going to be 0.12, all of it over 2A, so that is just 2, and that is negative 0.2 plus or minus square root of 0.16 over 2. And everybody knows that square root of 0.16 is 0.4. So this is negative 0.2 plus or minus 0.4 over 2. And that gives us two possible solutions. So lambda equals 1 was the first one. Anytime you have a Markov matrix, lambda equals to 1 is going to be one of the eigenvalues. And then the other one, let's start with plus. So 0.4 positive minus 0.2 is going to be 0.2 divided by 2 is 0.1. So lambda equals 0.1 is another eigenvalue. And then we have lambda equals, if we apply the negative, we have negative 0.6 over 2, that is negative 0.3. Okay. And then, you know the drill, we have to find out the eigenvectors corresponding to each one of those eigenvalues. So let me start with lambda equals 1. This is our original matrix. Remember our setup, we want A, B, C, so that equals, when we multiply after this with this matrix, we end up with A, B, C again, and then the ABCs move to the left side of the equation, which are ones, really. So we end up with, okay, so let's start with this guy initially to find the eigenvector corresponding to that. And I'm simplifying, I'm skipping a few steps. You know, we understand we're going to multiply by an ABC, a generic ABC vector equaling ABC, because ABC times 1 is ABC vector. And so when we move it to the left side of the equation, this guy becomes negative 0.8. So negative 0.8. The other two remain the same, 0.3, 0.5. Then 0.3, 0.3, negative 0.6, because we're subtracting 1, 0.3. And then 0.5, 0.3, and negative 0.8. So this is the matrix corresponding to A, B, and C. A, B, C. So I'm trying to find eigenvectors. But by moving the A, B, C corresponding to lambda equals 1, which would have been on the other side of this equation, we end up with just 0, 0, 0. And that makes things a little easier, I think, because then we can freely move this without worrying about the zeros, because the zeros, no matter what we do with them, whether we multiply them by a constant or add a multiple of one onto the other, we're still going to end up with zero. So we don't have to worry about this. We can do row operations to convert this into a row reduce echelon form. So this is what I'm going to start doing. It might be too late in the videos, but I'm going to put a little pause button, and that you're not going to watch that. I'm just going to show you when I show you this. That means I'm going to pause the video so I can do this on my own. You don't have to see, you know, all the ugly computations. But then, and then when I come back, now in the video, I'm not going to actually pause, but in the video, you're going to see just coming back with the row reduced echelon form of this matrix. So then we can continue finding the eigenvector. So I'm going to pause for a moment. Okay, so now I row reduced. It took me a while to do this, the matrix, and I ended up with this, which is an pretty nice simplifying. This tells us that A minus C is equal to 0, because we multiply this way, A minus C equal to 0, A minus C equal to 0, and B minus C equal to 0. And this doesn't really tells us anything. This tells us that 0 is equal to 0, and that is an identity, so that is irrelevant. That is like saying, well, I don't know, something that is true. Tomorrow it may rain or it may not rain. That's not saying anything. I know that's a silly example, but so A is equal to C, and so is B equal to Z, according to that. And that means that all of the vectors, all of the entries have to be the same. You know, if C is equal to B and C is equal to A, then A is equal to B. So everybody is the same. So the eigenvector corresponding to this lambda equal to 1 would be 1, 1, 1. So lambda equals 1. I guess we can label it as x1 is 1, 1, 1. It is not a bad idea to double check that actually that works. If we multiply with 1, 1, 1, oh yeah, they add up to 1 nicely. So that works. Okay. So we got our first eigenvalue and our first eigenvector corresponding to this eigenvalue. Then we want to find the eigenvector corresponding to 0.1. Oh, never mind this. We're not going to pause yet. So lambda equals 0.1, and we want to know the eigenvector corresponding to this guy. So the equation we start out with is similar. Well, what we're going to have is, what I mean is ABC equals 0.1 of ABC. So I'm going to start out with the same kind of equation. ABC equals 0.1 of ABC, because that is what the eigenvector does. And then when we move this to the other side of the equation, this is those diagonal elements are going to be reduced by 0.1. So we're going to end up with a 0.1, 0.3, 0.5, 0.3, 0.3, 0.3, 0.5, 0.3, 0.1 times ABC equals 0, 0, 0. And the reason why we do that, or the reason why I do that, is because that way I don't have to mess around with this column, with the augmented matrix. It's going to remain being 0 no matter what, because whatever row operation we apply to those rows or to this matrix, that's not going to affect this column vector. If those remained the way they were, 0.1a, 0.1b, initially 0.1c, then every time I do a row operation, I have to do the corresponding row operation on here. It's just more work for me. It's much cleaner just not to worry about this column, I think. Um, so, um, so let's row reduce it. Again, I don't think it's necessarily pleasant for you to keep watching the row reduction. So what I'm going to do is do it on the side. I'm going to pause this for a moment. You're not going to see the pause. The pause is going to be very short for you because I'm just going to pause it. I'm going to do the work, and you're not even going to notice. Okay, so now after the row reduction completely, we end up with this new matrix. So this reduces down to that. And that means that A minus C equals 0. And B plus 2C, 2C equals 0. Let's see. So that means A equals C. And B equals negative 2C. So if C equals 1, then we have 1, 1, negative 2 in the middle. So 1, negative 2, 1. It is a good idea to double check. So we claim this is x2. So this is lambda 2. Make sure you stay with your lambdas nicely. Be consistent. So we're going to label this as lambda 1, lambda 2, and this is going to be lambda 3. So this is our lambda 2. So this means that that is our x2. And I want to double check that actually it works the way it's supposed to work. 0.2, 0.3, 0.5. I'm multiplying A with this vector to make sure 3, 4, 3, 5, 3, 2, and to make sure we actually obtain what we are supposed to obtain. So 1, negative 2, 1. Let's see. So that means those two are going to add. So that is going to be 0.7 minus 6, minus 2 of the middle. So that is 0.1. And then those two added together is 6 minus 2 of those. That's minus 8. So that is negative 0.2. Negative 0.2. And then adding those two together, that is 0.7 minus 2 of those, that is 0.1. Yep. So indeed, and this is equal to 0.1 times, if we factor out the 0.1, we end up with 1, negative 2, 1, which works. That means that this is the lambda 2, this is the x2. So when we multiply A x2, we end up with lambda 2 x2, which is what is supposed to happen. So indeed, this is our lambda 2. Okay, rather, this is our eigenvector 2, x2 rather. Yeah. So now let's look for eigenvector number 3. So lambda 3, now I think it was negative 0.3. There it is, negative 0.3. And we want to find the eigenvector corresponding to that. And let me remind you, so we multiply the original matrix times ABC, and that's supposed to equal to negative 0.3 ABC. So when we flip that over to this side of the equation, we're going to be adding 0.3 to the main diagonal, and we're going to end up with 0.5, 0.3, 0.5, 0.3, 0.7, 0.3, and then 0.5, 0.3, 3 more is 0.5. And so we're going to solve this equation A, B, C equals 0, 0, 0. That's the way I go about it. Of course, you don't have to go about it that way. You can probably use some determinants, but in my opinion, that is a really long way to go about it for this kind of problem. So we want to row reduce this as in the previous examples. Let me pause for a moment to row reduce the matrix and come back. Okay, so I'm back, and we have this reduction. This tells us that A plus C is equal to 0. A plus C equal to, so they're opposite of each other. And B by itself has to be 0. And then this doesn't tell us anything, any additional information. So that means that A has to be the opposite of C. A equals the opposite of C, and that means that B still stays as 0. I have said in the past, in a past video, that because this is a free variable C, we typically put a 1 in there. I have a change of heart. I changed my mind about that because I really prefer to have 1 on my first entry of the vector. And we can get a 1 here if C is -1 to start with, because if C was -1, or let's put it the other way, C is equal to -A, so A could be A could be 1 and C could be -1, and that still will work. So I'm going to start preferring that only because if we do it the other way, as I had mentioned before, so I have a change of mind. Instead of making the C1, because that would cause the A to be -1, to me, it looks better to have a 1 on the first entry as opposed to a -1 in there. Now, if you didn't do that, you're still okay. Both are okay, as long as you stay consistent. Once you declare your eigenvector, stay with that eigenvector. So we have 1 for A, -1 for C, because they have to be opposite of each other. They have to add up to 0. Whatever they are, they have to add up to 0. So if this is 1, this has to be -1. If this is -1, this has to be 1. The middle one has to stay as 0. Now let's double check to make sure. I like to double check to make sure that my eigenvector, so I claim that this eigenvector x3 works. Let's go back to the original matrix, 0.2, 0.3, 0.5, 0.3, 0.4, 0.3, 0.5, 0.3, 0.2, multiplied, so this is the original A, with 1, 0, -1, gives us what we are supposed to get. Now let's see if that is true. So that means 2 minus 5, because we're doing the first one minus the last one. 2 minus 5 is -0.3, -0.3. 0.3 minus 0.3, 0. 0.5 minus 0.2, 0.5 minus 0.2 is 0.3. We can factor out the 0.3, or actually we can factor out the -0.3, even better, because the eigenvalue is -0.3, 0.3. Let me do that in the next line down here. So that is equal to -0.3 times 1, 0, -1. So we do have what we're supposed to have, which is that x3 equals lambda 3 times x3. It does work. X3 is equal to lambda 3 x3. That is exactly what the eigenvector is supposed to do. So that means that our matrix X, which will consist of the eigenvectors x1, x2, x3, will be, I have to go back to what x1 was. I think that was 111. Flipping through, yep, x1 is 111, 111. X2 is on my next page, and that was 1, -2, 1, 1, -2, 1. And then 1, 0, -1, 1, 0, -1. I need to check whether, I didn't check in advance whether this was going to be invertible. I'm going to use something like the Gauss-Jordan elimination. I'm just kind of checking real quick. We can eliminate those two. Let me pause the video so I can find out whether this is even invertible. I think it is, but I don't know for sure. So I'm going to pause for a moment. You're not going to see the pause to you, the viewer, because you're going through this video, is going to be nothing. But I'm going to check to see what the inverse of this matrix X is. Okay, I'm back. Boy, that took a while. Yes, X is invertible. This is the inverse. And that means that now we have all the components. We have the eigenvalues. The eigenvalues must be placed in the same order as the corresponding eigenvectors on the matrix X. And that means that A is equal to X d X inverse. So, and you should verify that indeed, if we take the original matrix, 0.2, 0.3, 0.5, 0.3, 0.4, 0.3, 0.5, 0.3, 0.2, that is indeed equal to this matrix, -2. So there's a bunch of ones here, -2, 0, and then 1, 1, -1 times this diagonal matrix with 1.1 and -0.3 in the main diagonal, and I missed the 1/6. 1/6. I'm going to put the 1/6 after 2, 2, 2, 1, -2, 1, and 3, 0, -3. 3, 0, -3, and that should be multiplied with 1/6. So that multiplies this matrix. It doesn't matter because you can move this scalar across everywhere, but I just want to identify it with this matrix. So A is equal to this. Now, what is the value of that? The value of that is that if we want to find A to the 10, instead of multiplying this A with itself 10 times, we have to multiply only X d 10 times, which is way easier because multiplying a diagonal matrix is easy. I'll show you in a moment. Times X inverse. X inverse. Yep. So this is equal to 1, 1, 1, 1, -2, 0, 1, 1, -1. Okay, so here's the deal. To do d to the 10, all we have to do, because this is a perfectly diagonal matrix, all you have to do is 1 to the 10, 1 to the 10, 0, 0, 0. 0.1 to the 10, 0.1 to the 10, 0. And then 0, 0, -0.3 to the 10. And then we multiply by 2, 2, 2, 1, negative 2, 1, 3, 0, negative 3, 3, 0, negative 3. And don't forget to multiply by 1/6. The 1/6 I'm going to do last because that is going to create a fraction. So if we want to know the probability after after 10 cycles, if remember, all of this started with 3 populations. And if those are the corresponding probabilities of migration from one population to another population, after cycles, whether they're years or seasons or whichever, days, weeks, the question is, what is the probability that if we start with P, we end up with in P? Or for that matter, we can, because we're going to end up with a full vector, the probability that if you start in P, where you're going to end up after 10 cycles. And these are probabilities. So that is the same thing as figuring out A to the 10 times 1, 0, 0, indicating we are starting on the first population P. Okay, so we're going to multiply those 3 with 1, 0, 0. So I'm going to move the 1/6. Well, the 1/6 is part of this x to the negative 1. So I just want to write x d to the 10 x inverse. There's the 1/6 in here times 1, 0, 0. And of course, we can multiply from left to right. It is faster if you multiply from right to left because there's fewer multiplications. Otherwise, here we're going to do 9 things. And then once we have this matrix, we're going to multiply 9 things again. And then we're going to do 3. If we multiply those 2, we get 3. And then you stay with 3. And then 3 again and 3 again. So instead of doing 9 and 9 and 3, we're doing 3, 3, and 3 all across. So this is going this way is faster. You still end up with the same answer. So there's no. So I'm going to keep that on hold. I'm going to write down the x to the negative 1, which has the 1/6. So I'm going to keep the 1/6 out because I don't want to deal with that for now. And we got 2, 2, 6, rather 2, 2, 2, 1, negative 2, 1, 3, 0, negative 3. And let's see what happens when we multiply with that. Well, that's easy. That's going to give us x. By the way, this is the matrix x. Should make it a little bigger. D to the 10, 1 over 6. And then we just, by doing this, we're just getting the first column, 2, 1, 3. So I'm going to move the 1/6 over to the left, 1 over 6. Keep the x there. D to the 10 will be this. So that is just 1, 0, 0, 0.1 to the 10, 0, 0, 0. Now, oh, by the way, this is bad notation. I can't believe I did that. This is super, super bad notation. This should be parenthesis. Whoa, I can't believe. Shame on me. This should be negative 0.3 to the 10. I can't believe that I did that. At least I fixed it, but still, make sure you have a parenthesis because we are doing the negative to the 10th, which means the negative is going to go away because we're going to have 10 negatives. So this is really 0.3 to the 10. Yep. And then we're going to multiply with 213. 213. See, these products are way easier than if we were to multiply the other way, the matrices across. So that is going to be 1 over 6. But just as well start writing what x is, because in the next, right now in the next step, I'm just going to multiply those two. So we have 1, 1, 1, 1, negative 2, 0, 1, 1, negative 1. And now let's see what this product is. So we end up with 2. And then the next one we get 0.1 to the 10. And then 3 times, that is interesting, 3 times 0.3 to the 10. Boy. Yep. So this is just a column vector. This number is kind of weird looking, but it is just a column vector. Okay. And that is, when we multiply all of that together, 1/6. Okay, so this is a column vector. Each one of the entries will be a little long because we're going to multiply 2 plus yeah, 0.1 to the 10 plus 3 times 3 times 0.3 to the 10. Okay, so that is the first entry. Second entry, 2 minus 2 minus 0.1 to the 10 times 2. Yeah, I forgot to multiply by 2, but that's easy to fix. Let's just multiply by the 2 after. So this number is going to be multiplied by 2. And then 2, whoops, 2, this is very, very interesting. As I'm thinking ahead, minus, rather plus 0.1 to the 10, 0.1 to the 10, and then minus 3 times 0.3 to the 10. Okay. Now let's understand what 0.1 to the 10 is first as we go about this. So 0.1 to the 10. Okay, so when we multiply 0.1 by 0.1, we are adding an extra 0 between the 1 and the point. So 2 means 1 0, 3 means 2 0, so 10 is 9 0. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is 0.1 to the 10. It's virtually 0, especially compared to the number 2. I mean, 2 plus this number or minus this number is essentially 0. If we multiply by 2, so 0.1 to the 10 times 2, that's going to give us 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 2. Still virtually 0. I mean, this is super, super small, tiny, 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 tiny. I mean, the thickness of a piece of paper, I don't know, it's somewhere in the neighborhood of 0.005 inches. So imagine that this is super small. This is virtually, this is 0. Mine, this is almost 0. 0.3 to the 10 is more complicated. I don't know if a calculator will be able to figure this out. How far we can go, 3 times, so that's 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, that isn't too bad. And we have 1, 2, 3, 4, 5. So this is actually 1, 2, 3, 4, 5, 59,049. Now this is virtually 0 again, although no, it's not. This is really, really 0. This is also close to 0. This is very, very tiny. So 8 to the 10, we're still trying to answer or finish an answer. 8 to the 10, 100 is going to be 2 plus that plus that. So 2 plus, 1/6 rather, of 2 point. And then we're going to add this, times 3. I forgot to multiply this by 3. So 5 times 3 equals 177, 147. So we're going to have 4 zeros, 1, 2, 3, 4. 177, 147, but yeah, we're going to add this one, so that's going to be 148. Okay. Then the next number will be 2, well, that is 1.9. We're going to subtract 2 of those, so 999999998. There we go. And then the next number will be we gotta add this much. We gotta subtract 3 times this much. So let's see if I can do the math with this little calculator. So minus 1, 1, 2, 3, 1, 2, 3. Yeah, I think I can, if I'm not mistaken. So we're gonna have 1 point, that's 6. So 1, 2, 3, 4, 8, 2, 2, 8, 5. Should be 5, 3, but we're going to add one of those, so 4, if I'm not mistaken. Yep. Let's see. I'm going to use a bigger calculator, a more powerful calculator. Let me do that off time of video so that you don't have to watch these painful computations. I'll be right back. Okay, I'm back, and here are my computations. It took me a while to do these computations, and I have to trick the calculator. By the way, this is wrong. I had moved those two. But here are the actual probabilities. So if you start in town 1, the probability that you're going to end up in town 1 after 10 cycles is going to be almost a third, exactly a third. By the way, I already multiplied by 1/6. So it's almost a third. All of them are almost a third. So even though we are moving around, and it looks like the populations here, by the way, are exchanging, but then again, we don't know who. So let's say you start in Q and you move to P, but we don't know whether you're going to keep moving or you're going to stay a few times or you're going to move. We don't know anything. But after 10 interactions, this becomes quite stable, by the way. The more interactions we get, the closer we're going to get to exactly 1/3. In fact, that is the next question. What happens when we have an infinite number of interactions, of cycles? Now let's remember the question. The question here, the second question we wanted to ask is, what is the probability that if we start in P, we end in P after 10 cycles? Now that I think about it, 10 is kind of excessive, but the answer is right here. The probability is 33.33, and all of those decimals after percent. So it depends how you want to put it, but let's write it down. Since we have all those numbers, might just as well put them. So 33, 1, 2, 3 threes, and then 62. So 3, 3, 62, and then 858, 858%, which is virtually 33%. I mean, rather 33 and 1/3%. So there's a 1/3 probability that we will end up in, if we start in town 1, that we'll end up in town 1. There's exactly 1/3. After 10 cycles, after moving things around, if things are random, not random, if things have these probabilities. Yeah, that is very, very interesting. Oh, how about infinity? Okay, so we can generalize, and okay, so a to the n, 1, 0, 0, all right, is equal to, let's go back a couple pages. I'm going to go back a couple pages. Here, it is going to be equal to 1, 1, 1, 1, negative 2, 0, 1, 1, negative 1, which is our x. Now here's the key. Here's where the n shows up. It is going to be 1 to the n, 0, 0, 0, 0.1 to the 10. No, to the n, 0, 0, 0, negative 0.3 to the n. This time I did not forget the parenthesis. You know, I always tell students not to do that, and that's why I feel so embarrassed to do that in the previous here. I initially did not have the parenthesis. And then we're going to multiply with 1/6. So the multiplication has to continue down here. And then we're going to have 2, 2, 2, 1, negative 2, 1, 0, 0, 3 times 1, 0, 0. Okay. Yeah. I'm hesitating because I see a 1 here. Anyway, when n goes to infinity, and it makes sense to have infinity if we know things are going to converge. And this is what I mean. 0.1 to the 10 was virtually 0. And imagine to the 20, it's like 19 zeros and a 1. And to the 100 is 99 zeros and a 1. So this at infinity is going to vanish. It's going to be virtually 0. It's going to get smaller and smaller and smaller and super, super small. It's like an asymptote. And we're going to get to 0. In fact, it is an asymptote. So asymptotically, we're going to end up with 0. This guy, when n goes to infinity, this is going to go towards 0 when n goes to infinity. And 0.3, even though it's negative and it is going to alternate between positive and negative, it is also going to go to 0. It's going to take longer. Notice how we have about 5 zeros and then a number. So it might take a while, you know, in order to end up with 10 zeros and a number, we might have to go all the way to 0.3 to the 20, perhaps. But eventually, we're going to end up with 10 zeros. And yeah, in fact, if you multiply this with itself, we're going to end up with close to 10 zeros. It's probably going to be less than 10 zeros, but it's going to be for sure more than 5 zeros. And then every time we keep multiplying by 0.3, this is going to get smaller. See, think about this. 0.3 is about a third. So every time we multiply by 0.3, we're taking a third. So a third of this is going to get reduced to, I don't know, like close to 20, because this is close to 60. So 20 and something. And then that is going to be reduced after 0.3 again, multiplying by 0.3 to 0.7 or so. So there's going to be a 0 showing up every 0.3 for sure. Yeah. Well, about, it's not exact. Every 2.3s, there's about going to be another extra 0 that is going to show up. So these numbers are going to be pushed away, and there's going to be more and more zeros causing this again to be asymptotic towards 0. So if n is infinity, this guy is going to go to 0 as n goes to infinity. So a to the infinity is going to be, I'm just going to put x. This matrix is going to become 1, 0, 0. Okay, now I'm okay, because I was a little worried. There we go. And then x inverse. So when we multiply with 1, 0, 0, let's see what happens. And again, let's multiply from right to left. So multiplying those two, we don't have to worry about this. We end up with 2, 1, 0, 2, 1, 0. And then, so a to the infinity times 1, 0, 0 equals x d to the infinity, which is going to be 1, 0, 0, 0, 0, 0, 0, 0, 0 times 2, 1, 0, 2, 1, 0. Yeah, when we multiply those two, we get that. Okay. And then we still have to multiply this, so that is going to be 2, 0, 0. So that is 1, 1, 1, 1, negative 1, 1, 1, 1, negative 2, 0, 1, 1, negative 1. Let me double check. 1, 1, negative 1. Yep. Times, when we multiply those two, we end up with 2. So this is this guy. 2, 1, 0. And let's not forget the 1/6. The 1/6 should be here. 1/6 is part of the x inverse. So, and I'm starting a new equation here anyway. So 1/6 equals 1/6. 2, 3. That's worrisome because we're supposed to end up with 1, 1, 1. Let me pause for a moment and see where the mistake is. I'll be right back. Okay, I'm back. And yeah, I made 2 little mistakes. I guess I'm getting a little tired. No, that shouldn't be an excuse. This is a 3. I missed that. But that does not have any effect on this. Let's see, when we multiply those two, we end up with 2, 1, 3. So this should be a 3. But then when we multiply with this matrix, the only thing that multiplies is the 1. So we end up with 2, 0, 0. There we go. And then when we multiply 2, 0, 0 with this matrix, we end up with 2, 2, 2. And then when we multiply through, we end up with 1/3, 1/3, 1/3. Yeah, so that is the probability, the corresponding probabilities at infinity of the populations as they move around different places. And you can do that with many different kinds of populations. It doesn't have to be individuals, live individuals. It can be anything that moves around. So there is the answer. Oh, let's answer the question. The question was the probability that if we start in P, we end up in P after an infinitely many cycles, and the answer is 1/3. Please do not put 33% because that is an approximation. We want to be precise. So we don't put the percentage, we just say 1/3, which is exactly the same thing as 33%. So that is the answer to that here. Because of all the decimals, I choose, and if you don't want to put the percentage, just move the decimal point 2 more places to the left, and then the answer is still good. And here 20% or 0.2, either one is good. All right, so this does it for a 3x3 not system of equations, 3x3 Markov matrix.